Alright, so in this problem, we are told about a vertical container, which I have crudely drawn with MS Paint here. And we are told the dimensions of its surface area, or the dimensions of its base. And it is 14 centimeters. So I'll write down 14 centimeters right here. By 17 centimeters. We are not told the height of the container. But we are told that it is filled with identical pieces of candy, and each candy has a mass, I'll call the M sub C for mass of the candy, of 0.0200 grams. And each piece of candy also has a volume, call that V sub C, of 50.0 cubic millimeters. We're told that this container is filled up with the candies to the point where the empty spaces between the candies is negligible. Now, we are told that the container is being filled up with candies to the point where we're given the rate of change of the height of the candy in the container. The height of the candies in the container is increasing at a rate of 0.250 centimeters per second. And because this is a rate of change of the height, I'll call this dH over dt, because it's a rate of change, similar to the way that a derivative would be written. Now, we are asked to find the rate of change in kilograms per minute of the mass, the total mass of the candies in the container. So with this information we're given, how are we going to do that? Now, we're looking for the rate of change of mass with respect to time. So let's call that dm. I'll write that as a big M to represent the fact that this is the total mass of the candies in the container. And it's dm over dt. We're looking for this. Now, because we are looking for a rate of change, and we are already given a rate of change of a component of this, we're given the rate of change of the height of the candies in the container, it might seem logical that we would want to find some link, some connection between our dm over dt with the dh over dt. So let's try and see if we can break apart this mass component right here. So we know that the big M, the mass, the total mass of the candies, is going to be equal to just the mass of all the candies together. But let's see if we can break this apart. So if the mass is the total mass of all the candies, then together, and if we're assuming that the empty spaces between the candies are all negligible, then we can almost imagine that all the candies put together are a single entity, as if we're imagining one large mass of candies put together with the height slowly increasing. So if we want, we can imagine mass in terms of density. So we know that density is equal to, in any case, density is equal to the mass of something over the volume of that thing. And that's how you get the density of that thing. So logically, we know that means that the mass, of course, is going to be then equal to the density times the volume. And we can apply that here as well. We can write the mass of this rising height of candies in terms of the density of the candy multiplied by the volume of the candy. And although we're given the volume of one piece of candy, we're looking for the total volume of the candy filling up the container, which could probably be better represented in the variables we have as the volume of a rectangular prism, like what we have here, is going to be equal to the cross-sectional area multiplied by the height, as such. So when we have a derivative of the big mass with respect to time, we can rewrite this as d of, and then density times the cross-sectional area times the height over dt. And because we have dH over dt, now it starts to become much more clear how you can relate the rate of change of height into this little formula we're starting to build here. So let's take our density and the cross-sectional area out, because we can see these as constants, basically. And so let's put them on the outside, so that our formula then becomes the density times the cross-sectional area times dH with respect to dt. And now we have our entire formula here in terms of variables that we can solve for with the numbers we're given in one way or another. So the first thing let's try doing is let's try finding the density of the candy, or the density of a piece of candy. And the density, of course, is going to be constant all over the container, assuming that we, again, negate the empty space between the candies, and assume we're dealing with a mass of candies, is basically how we're idealizing it. And the density is going to be equal to, of course, its mass over volume. And we're given the mass of the candy and the volume of a piece of candy. So the mass of the candy is 0.02 grams. So let's write that in. 0.0200 grams divided by its volume. And the volume of a piece of candy is 50 square millimeters. So 50.0 mm cube. And plugging this into your calculator, you'll get a density of 4.00 times 10 to the negative 4th power of grams per cubic millimeter. And now, let's do a quick conversion here, because since the problem asks us to find a rate of change in kilograms per minute, let's quickly convert the grams into kilograms. And let's also change cubic millimeters into an easier to work with unit as well. So keep in mind that we're given the change in height in terms of centimeters per second, and also our dimensions for the cross-sectional area of the container are also given in centimeters. So let's change the cubic millimeters into cubic centimeters. So let's take this. Let's have our 4.00 times 10 to the negative 4th grams per cubic millimeters. And let's do a chain link conversion on this to convert into kilograms and cubic meters, or cubic centimeters. So first things first, there are 1,000 grams in a kilogram. So let's put the grams in the denominator to cancel out. As usual, the chain link conversion, you should know how to do this by now. And then let's do the conversion from millimeters to centimeters. And of course, there are 10 millimeters in a centimeter, and to 1 centimeter, and cube the whole thing, so that we get a cube, so that we know that we are converting using cubic units here. And now we'll have a density of, actually, funnily enough, we get the exact same number, just with different units, because this ends up becoming divided by 1,000, and we have 10 cubed, which is also 1,000. So we actually end up dealing with the same number in the end anyway. But either way, it's 4.00 times 10 to the negative 4th of kilograms per cubic centimeter. That is our density. Now let's try and find the cross-sectional area, the next little component of our formula here. Now the cross-sectional area is going to be pretty easy to find, because the area is just equal to length times width, or however you want to describe that. So it's just going to be 17 centimeters times 14 centimeters. So let's write that out then. So area is equal to 14.0 centimeters times 17.0 centimeters, which is equal to about 238 cubic centimeters. There we go. And now we have found every single individual component of our formula here that we created. So now to get the final answer for the change of mass with respect to time, we'll just want to plug in all our little variables. So first the density, which of course we found as 4.00 times 10 to the negative 4th kilograms per centimeters cubed times the cross-sectional area, 238 squared centimeters, times the height, or the change in height with respect to time, which is 0.250 centimeters per second. And now that we have all this set up, now we can plug this into our calculator, and we'll get a rate of change of mass of 0.0238 kilograms per second. And because the question asks us to write our answer in kilograms per minute, let's do one final conversion. So we're going to convert from seconds to minutes. So that is 60 seconds in a minute. So that is 60s in the top, divided by 1 minute. And we get a final answer in the proper units of 1.43 kilograms per minute. And that is the rate of change of the mass of candies in this container.